Bootstrap confidence intervals are an alternative to using statistical theory and the central limit theorem. Bootstrap methods make fewer assumptions about the population. If the data do not follow the normal distribution, confidence intervals can still be estimated with bootstrapping. There's no statistical theory for confidence intervals for some statistics, and in these cases, bootstrapping can be used to estimate confidence intervals. Bootstrapping is based on resampling the data in the sample with replacement. And bootstrapping is feasible only with the use of software to automate the heavy computation that resampling methods require. Statistical inference uses the bootstrapped distribution of a sample statistic, and the bootstrap distribution is one way to find the approximate sampling distribution using just one sample. Here's a simple example of resampling. This is a marcode that resamples data with replacement. The first line uses the C function to assign the data to an object named data. The second line finds the mean of the data. Next, set.seed2 controls the random sampling process. Next, an object is created named sample.1, and the sample data size5 replace true command selects a random sample of 5 items with replacement. Wrapping the entire line in parentheses computes the resampling and displays the 5 values in sample 1. The next line does the same thing for sample.2, and then the next 2 lines find and display the sample means. Finally, the 2 samples are averaged to find the average of the averages. This is the output. The mean of the actual sample equals 14.8. Sample.1 contains 20, 10, 2010, and 17. Sample 2 contains 2010, 12, 15, and 10. The average of the 2 samples is 14.4. Bootstrapping uses a process like this, but instead of using 2 resamples like in this example, bootstrapping typically uses thousands of repetitions. This R code finds a bootstrapped confidence interval for the population mean. First, we load the readr package, and then we import the alert time data that's on the class Blackboard site. I've saved the data to my H drive. The next line uses the $sign operator to explicitly tell R the data frame named myData contains the variable named time with an uppercase T. The data is assigned to an object named X. I created an object named sampleMean. In this line, function creates a function, and the function has 2 arguments, x and I. And we have an opening curly bracket, and then we have mean parenthesis x with an I in square brackets. And in this case, the I is an index. It's used to refer to a specific line in the data during the resampling process. Then we've got the closing curly bracket. Library boot loads the boot package. I created an object named B. The boot function has 3 arguments. The data is the first argument. The statistic we created, sample mean, is the next argument. And then R equals 10,000 is the number of repetitions we're going to use. Plot B plots the result. Boot.ci has 3 arguments. B that was defined earlier. Confidence interval equals 0.95 tells R to find the 95% confidence limits. And type equals VCA defines the type of confidence interval you want. The plots on this slide look like the result from a normal distribution. The boot package provides several different types of confidence intervals. The VCA interval, and this stands for bias corrected and accelerated, is generally considered to be the most accurate. Bootstrapping can be used on any statistic you can calculate. It does not require a normal population, even with small sample sizes. Computer simulations have shown that the shape and spread of the bootstrap distribution are close to the shape and spread of the sampling distribution. Thanks for watching, and please let me know if you have any questions.